Good morning, my dear friends. This is the third part of the video for probability. This video discuss the examples of the above video, isn't it? The previous video. So please subscribe and like symbol to this video and also give the comments. So let's move the examples. For example, first one complementary events. When a die is thrown, occurrence of an even number 246 from the dice and odd number 135 are the complementary events, isn't it? So this is very clearly given the example. When a die is thrown, occurrence of an even number, so the result will be 246, isn't it? So the odd numbers 135 are the complementary event of the given event, isn't it? Let's move the next one. Exhaustive events. While tossing a dice, the possible outcomes are 1, 2, 3, 4, 5, and 6. And hence, the exhaustive number of cases is 6. When you take a coin, tail and head are the output or outcome of the given event, isn't it? So there are two events. There are two exhaustive numbers, isn't it? For a coin. For a dice, there are 6. For a coin, there are 2, isn't it? For a pack of card, 52, isn't it? Okay. Let's move the next one. Equally likely events. If an unbiased coin or dice is thrown, each face may be expected to be observed approximately the same number of times in the long run. So, if you take a coin, there are two outcomes. So probability of getting head 1 by 2. Probability of getting tail, it is also 1 by 2. So the same uh, output, isn't it? If you take a dice, there are 6 numbers 1, 2, 3, 4, 5, 6. So if I get probability of getting number 2, 1 by 6. If I getting probability of number 5, 1 by 6. Okay. So all the output are the same, isn't it? It is called equally likely events. Now we move to independent and dependent event. First one, dependent. The example is if a card is drawn from a pack of playing cards and it is not replaced, then this will alter the probability that the second card is drawn, isn't it? If a card is drawn from a pack of playing cards and it is not replaced, this will alter the probability that the second card. So this is called a dependent. And the next one we move to, if a coin is tossed twice, the result of the second throw would be in no way be affected by the result of the first throw. This is called a independent. So go back to the definition of independent and dependent. It is not affected, it is independent. It is affected by dependent, isn't it? Okay. Mutually exclusive events. If a single coin is tossed, either head can be up or tail can be up. Both cannot be at the same time. So it is very clear. Any one of the output can be existed, isn't it? If you toss a coin, tail can be existed or head can be existed. Both cannot be existed. So it is called a mutually exclusive events. And very important theorem, addition theorem from probability. If two events A and B are mutually exclusive, the probability of the occurrence of either A or B in the sum of the individual probability of A and B. So P of A or B is equal to P of A plus P of B, or P of A union B is equal to P of A plus P of B. So this is the statement of addition theorem from probability. So we are going to prove this result. If an event A can happen in any A1 ways and B in A2 ways. So there are two events they are taking. One is A, another one B. There are how many ways A can be happen? A1. A2 ways B can happen. Then the number of ways in which either event can happen is A1 plus A2, isn't it? And the next one, if the total number of possibilities is n1, then the definition, the probability of either the first or the second event happen a1 plus a2 by small n, okay, is equal to, what about a1 plus a2? So a1 ways can happen capital A, a2 ways can happen capital B, isn't it? I'm going to add these two events, a1 plus a2 divided by total number of uh, times, isn't it? Possibilities. So it can be splitted a1 by n plus a2 by n. So already we know probability of occurring capital A is equal to a1 by total number of outcomes, that is small n, isn't it? Small n, what do you mean by small n? Total number of outcomes. What about small a1? Possible outcome for capital A. What about P of B is equal to A2 by N? What do you mean by A2? Possible outcome for capital B, isn't it? Divided by number of total number of outcomes small n. So A or B, probability of A or B can be written as probability of A plus probability of B, or P of A union B is equal to P of A plus P of B. It is proved. So very important theorem, so easy. So these are the ways we can prove addition theorem from probability. So let's move one example for addition theorem. One card is drawn from a standard pack of 52. What is the probability that it is either a king or queen? So take a card. There are 52 cards in a pack. So the question is, what is the probability that it is either king or queen? Isn't it? So let us solve this problem. See this solution. There are 4 kings and 4 queens in a pack of 52 cards. So these are the classification. How many queens in the card or how many king in the card? Pack of card, isn't it? So there are 4 for each, king as well as queen. The probability that the card drawn is a king 4 by 52, isn't it? Then the probability of card drawn a queen, it is also 4 by 52. At next line, since the events are mutually exclusive, isn't it? So this is a very important condition. Since the events are mutually exclusive, what does it mean? It is not affected. Okay, well, or we can say both cannot happen simultaneously. So the probability that the card drawn is either a king or a queen is equal to. So you see, this is the keyword or. If you get or in a probability, put plus sign. So 4 by 52 plus 4 by 52 is equal to 8 by 52. A or B. A means king, B means queen, isn't it? So the simplification is 2 by 3. So it is over. So this is the result of the problem. One important note, when events are not mutually exclusive, P of A union B can be written as P of A plus P of B minus P of A intersection B. So please remember, very important formula. P of A union B is equal to P of A plus P of B minus P of A intersection B. Or P of A or B is equal to P of A plus P of B minus P of A and B. So, and for intersection or for union. Please remember. Thank you, my dear friends. Thank you. Thank you so much.